So we continue now the previous video. So we saw Gleason's theorem, Cohen-Spectral corollary, or however it is that it is pronounced. Now let's develop a bit more the consequences of Gleason's theorem. We will denote as capital T H to the set of all positive trace class operators of trace 1, which is the density matrices. Now, for the following, we need the notion of a convex set and of extreme elements there. I will not go into the details, but this is a vector space. This is a space of operators, and you can define what it is a linear combination, and it's called convex if these properties are satisfied. And convex combinations have extreme elements, and that will be relevant for the following. What are the extreme elements in TH? Recall that this is the space of the density matrices, which is indirectly the space of all possible quantum probability measures. So TH is convex in the space of trace class operators, and the extreme points in TH are those of the form for a vector in the Hilbert space normalized. So basically this is a one-dimensional projector on the one-dimensional line defined by this vector. That's what the extreme elements or extreme states are in TH. So basically they are determined by a vector here. But in fact it is not just a vector, because the actual state is this, the TH, which is the projector. So what we have really is a bijection between the extreme states of this form and rays on the Hilbert space. So these states are called the pure states, and the others mixed states. So you can see we can recover then one of the usual axioms of standard quantum physics, which is that the states are rays in a Hilbert space. Now in classical probability you can also do something similar, and the pure states are given by the Dirac measures, and the mixed ones are general measures. Dirac measures are measures of the type that were prohibited by the Cohen-Spectral corollary, which are measures that only take values in 0 or 1. Now, but in classical probabilities, what happens if we add 2 points to get a third point? We cannot do that in a general differential manifold, because it is not a vector space. So you cannot just add 2 points to obtain a third point. and Dirac measures are in a bijections with points. And so if you perform this, if you add two Dirac measures at the level of measures, you will not obtain another Dirac measure, because that will mean you will obtain a third point. So when you add two Dirac measures, you always obtain a mixed state, a general measure. But in quantum physics, you can go to the Hilbert space and you can indeed add two rays to get a new third ray because of the linearity of Hilbert space. And you get, of course, a new pure states. And this is something new in quantum physics. And of course, this is just the superposition property of pure states in quantum physics. And in the case of compound quantum system, this of course gives rise to the entanglement of states. Now, since we now know the form of pure states, we can state the Born rule for pure states. So consider a pure state and an orthogonal projector. So the probability of P for that state, you just calculate the trace and you obtain this. If in addition the projector is of this form, one-dimensional projector, when you calculate the trace you get this, which is the standard Born rule for the transition probability between two rays. And well, this is this is basically an elaboration of the Cohen-Specker corollary. Now let's go back to the classical case to discuss how are properties represented there, or what are sometimes called the observables of the theory. So we will denote in this form the phase space time in the Hamiltonian formulation, which is basically a fiber bundle on R, which represents the Newtonian time, and each fiber there is of course for a symplectic manifold that represents phase space at time t. Now consider H to be a possible fact about a mechanical system. So for example, it could be a fact about properties valued in R of the system. For example, we consider the position with respect to some coordinate system in space. A possible fact is that the position is equal to 5 meters. That could be a fact about the system. That in that fact, the position is equal to 5 meters. So consider now a subset in which of phase space points of sharp states in which the theory predicts that these facts will surely occur. In the previous example, the fact is of course a function, the coordinate is of course a function from the phase space to R, and which is the function that mathematically represents position. And so this E is made up of all these state S such that the position applied to to those states gives us 5 meters. So we can see that the interpretation of the elements in the Borel sigma algebra of phase space is just as possible facts about the systems in this form. So that's why the elements in Borel sigma algebra of this type of probability theories are called the events of the probability theory, since they represent facts about the system, possible facts. And furthermore, as we mentioned, this fact could be also a bit about properties of the system in the sense of functions from phase space to R. Now, so these properties are functions from a measurable function from phase space to R. So let's try to characterize that now in lattice theoretical terms. So consider the Borel algebra of the real line. Whoops. And take an element B there. So if we take the inverse image of this B via this function, we will obtain, of course, an element in the Borel algebra, sigma algebra of phase space. So to each Borel element in the real line, and for a measurable function, we can obtain a Borel element of phase space. That is a possible event. So the question, of course, is to what fact about the system this event corresponds to. And the answer is very simple, is that the fact in which the value of the property represented by f is contained in B. Because by definition S will be in this inverse image if f applied to S is in B. And so we can see that we can describe the properties now not as functions but as a collection of Borel elements in phase space parameterized by Borel elements of the real line. And in fact, we will ask actually more. We will ask this collection to be a Boolean sigma subalgebra of the Boolean algebra of the sigma Boolean algebra of the Borel algebra of the phase space. And this assignment V to EV to be a homomorphism of Boolean sigma algebras between the Borel algebra of the real line and the family of facts on phase space parameterized by B. So we can see all of this is just happens in the lattice. We can directly take this definition and import it to quantum probabilities. So how do we represent a property valued in the real line in a quantum system? Well, simply as a family of facts, H, that is of projectors, parameterized by elements in the Borel algebra of the real line, and which are the values where the properties, the values of the property will be contained. And thus we get a family of projectors parameterized by this B in the Borel algebra of the real line. And we ask it again to be a Boolean and sigma algebra of projectors as a sublattice of the lattice of all projectors, and the assignment to be a homomorphism of Boolean sigma algebras. And so this sublattice and this homomorphism of Boolean sigma algebras will be our way of characterizing a property which takes values in the real line in a quantum systems. So it is identical to the classical case, but now we have projector here instead of Borel elements of phase space. Okay. This assignment is what is called in spectral theory a projector valued measure, because it is indeed actually a measure on the Borel algebra of the real line, with the exception that it is valued in the set of orthogonal projectors rather than in the segment zero closed segment of the real line. That's why it's called projector valued measure. So, but I mentioned that measure theory was a generalization of the theory of integration. So, what happens if we make a Lebesgue integration of one of these things? What do we get when we integrate a projector valued measure? The answer is that we get this, a self-adjoint operator, generally unbounded. So one has to be very careful with it, because the domain is not the full Hilbert space and is not a continuous operator. Even when it is a linear operator, it is not continuous in the topology of the Hilbert space. That's one of the key differences between finite dimensional Hilbert spaces and infinite dimensional Hilbert space. So we get an assignment: projector valued measures always give us self-adjoint operators by this integration, these Lebesgue integrations. However, the assignment doesn't need to be neither injective nor surjective. But now we have the fundamental von Neumann's general spectral theorem, which states that given a self-adjoint operator, then there is always a unique projector valued measure such that when we integrate it, we get the original operator. And furthermore, the spectrum of the operator is the support of the PVM, the projector valued measure. So we only need to integrate on the spectrum, because that's where this is non-zero. So the existence allows to establish the surjectivity of the previous assignment, while the uniqueness establishes the injectivity. So we have a bijection between projector valued measures and self-adjoint operators. And since we used projector valued measures to define properties of a quantum system, we get the usual axiom that properties of a quantum system are described by self-adjoint operators, and that the possible values of those properties are the spectrum of that operator. But we started with much more plausible definitions. We just took the classical definition of properties as a functions on phase space. We reinterpreted that in lattice theoretical terms we used that reinterpretation in lattice theoretical terms to impose that definition on the quantum case, on the quantum lattice, and by von Neumann theorem we get automatically the characterization of these properties as self-adjoint operators and where the values are in the spectrum of that operator. Now let's see now some examples. If you consider a compact self-adjoint operator, then Hilbert's theorem states that the operator's eigenvalues are discrete and that the operator can be decomposed in this way, and where these are the projection to the eigenspaces for that eigenvalue. The dimension of those eigenspaces is always finite and is called the multiplicity of the eigenvalue. We can use these projections to define a spectral projector in the following way. We just sum over R in this way. And if we integrate this projector value measure, we obtain the original operator. So, by the uniqueness established by the spectral theorem, this PVM is the PVM that is uniquely associated with the self-adjoint operator. Furthermore, by using some of the properties established by the spectral theorem, we can see that using this projector value measure, we can see that this operator only has a point spectrum, and that it's given by its eigenvalues, and that its continuous spectrum is empty. Which are of course very well-known properties from a first course in quantum mechanics. And now suppose that we have a non-degenerate eigenvalue, so the projector will be just one-dimensional, and we get an basis of eigenvectors. And so we can calculate via the Born rule what's the probability for this event in a state T of this form, a pure state, and of course we get the usual rule. Now let's go to a more interesting example, which is the following. A self-adjoint operator which has a purely continuous spectrum, then the operator cannot have any eigenvector. Because an element that belongs to the point spectrum, if and only if is an eigenvalue of the operator, and if it is an eigenvalue, it has an eigenvector. Note that the notion of spectrum is much more general than just the set of eigenvalues. We can have a continuous spectrum even when we don't have any eigenvalues and eigenvectors. And the typical example is the multiplication operator in the Hilbert pairs space L2 on the real line with the Lebesgue measure, which is of this form, just the multiplication, and almost everywhere, of course, and since this is an unbounded operator, the domain is given by this, and this of course is just a proper subset, a dense proper subset of the whole Hilbert space. And you can indeed check that this is unbounded by this argument, and that the domain is strictly contained in the Hilbert space and is not equal. And you can indeed see that if you try to establish an eigenvector, you will end with a function that is 0 almost everywhere. But that means that this function belongs to the equivalence class that forms the null vector in L2. So, with this supposed eigenvector cannot exist. But this will not be a problem because we are using von Neumann's spectral theorem. So we can still, even when we do not have eigenvectors, we can still define a projector valued measure in the following way, where this is the characteristic function of the set B. And when we integrate this measure, we of course obtain the operator A. And by the uniqueness of the spectral theorem, we know then this spectral measure, this measure has to be the unique spectral measure associated with this operator. And we can indeed now use this spectral measure to see that this operator has an empty point spectrum, and that its continuum spectrum is just the real line, as we expected. And all of this can be done with von Neumann's theory, without the need of eigenvectors. And now, by using the previous Born rule, we can calculate using that projector valued measure for a pure state what's the probability, and we get, of course, the usual integral of the wave function squared on the volume where we are asking our particle to be. So we recovered all of that, and without using Dirac's notations that pretends that eigenvectors exist. We used instead the existence of the projector valued measures established by von Neumann's general spectral theorem for self-adjoint operators. So this concludes our derivation of the basics quantum mechanics axioms from much more plausible geometric and probabilistic axioms than the ones used in a first course on quantum physics. And this point of view of non-distributed lattices is closely related to the following point of view, which is an alternative point of view to rederive all of these, the appearances of Hilbert spaces, etc. But they are closely related because in the probability case, we had the classical case is Boolean, distributive, and the quantum case is non-Boolean and non-distributive. And in the non-commutative geometry approach, we will have something similar. So let's first define a C-star algebra, which is a Banach algebra over the complex numbers with an involution, and that satisfies the key property, which is the C-star property, which is this. For example, if X is a compact topological space, then the continuous functions from X to the complex numbers with the pointwise product and norm defined in this way is indeed a C-star algebra. an example of a C-star algebra. And note that this product is of course commutative. And now we have a key result, which is the following. The Hilbert duality, which states that if A is an abstract commutative C-star algebra with unity, then there is a compact topological space such that the original abstract algebra is isomorphic to the algebra of continuous functions on this compact topological space. So, if we have commutative C-star algebras, we cannot go beyond just the usual compact topological spaces. Very similar to the cases that when we had abstract Boolean sigma algebras, we got an isomorphism with Boolean sigma algebras coming from sets. Now let's define the notion of an algebraic state, which is just a linear map from the algebra to the complex number, which is positive, which means this property is satisfied, and normalized. An example, for example, is if you have a Borel probability measure on a compact topological space X, then the following is an algebraic state on this algebra of continuous functions. The state applied to the function is just the integral with respect to the measure of the function. But now, if so, keep in mind the Hilbert duality, so we can say that classical probability theory is captured in some sense by the theory of abstract commutative C-star algebras and algebraic states on it. So we can consider a general abstract non-commutative C-star algebra and algebraic states on it, and will correspond to a non-commutative generalization of the concept of probability theory, which is something very similar to what we did of considering now non-distributive lattices and probability measures there as a generalization of a standard probability theory. So, how does such a theory looks like a non-commutative generalization? And due to the following results, it is simply quantum mechanics, because the Hilbert-Neymark theorem establishes that if A is an abstract C-star algebra, likely non-commutative, then there is a Hilbert space such that it is isomorphic to a C-star subalgebra of the C-star algebra of all bounded operators on this Hilbert space H. So we recover Hilbert spaces via in the C-star algebra approach. And if we have a density matrix, we can define an algebraic state here on this algebra by taking the trace, which is of course the expectation value of A in this state. So we recover the usual quantum formulas, but now seen as algebraic states. So this finishes the second part of this video.